Well, hello there, and welcome to the Evergreen Building at the College of Southern Idaho, the geology classroom where I spend a lot of my time. And we're gonna launch our next rock identification video today by introducing you to the sedimentary rocks. And so we're not gonna look at a lot of rocks today. We're gonna go over some big concepts. And this will then springboard us into being able to look at different types of sedimentary rocks, again with the whole goal here that we're helping you with your own rock identification when you're out on your own adventures and hikes and whatnot, or maybe looking at some samples you might have in your own collection. So I want to give you some some framework and some ideas, some concepts to kind of work from as we can kind of get into this next arena of the rock world. We've spent time already looking at the igneous rock, so I thought it would be good to, as we launch the sedimentary rock video series, I thought it'd be good to kind of come back to the rock cycle and just make sure we're all on the same page here. So we've looked at what happens when magma crystallizes, whether it's underground or at the surface, with our igneous rock series. And now as we kind of move forward here a little bit, what we're mainly going to be focusing on is what happens to any existing rock. So it could be igneous, metamorphic, or even an already existing sedimentary rock. But what happens to those rocks when they are at the surface, when they are weathered, which means that they're broken up into smaller pieces by different processes, when those weathered particles or sediments are transported by various mechanisms, could be ice, could be wind, could be water, which encompasses both, rivers and streams, lakes, I suppose, ocean processes. Ultimately, those sediments that get transported have to stop somewhere, and so they get deposited. That's their final resting place. So that's then the deposition of sediments. Those sediments can then be buried or compacted or cemented together by various means. We call that lithification. And then you end up with sedimentary rocks. And so that's what we're going to focus on today with our introduction to sedimentary rocks. Kind of giving you the context here again of what we're kind of look at moving forward a bit. So what else can we say about sedimentary rocks? Well, they're incredibly prolific at the Earth's surface. They cover most of Earth's land surface, about 73%. So chances are, if you're wandering around in your community, there are sediments or sedimentary rocks to be seen nearby you. But realize that the sedimentary rocks are a very small percentage of the volume. So while they cover a large area, they don't extend very deep in most places. Maybe a few thousands of feet in some places. The sedimentary cover could extend tens of thousands of feet, but that's a pretty small amount when we look at the grand scheme of things in terms of the thickness of the Earth and the crust of the Earth. Sedimentary rocks, unlike the igneous and metamorphic rocks that we've looked at, have a distinction in that they form at or near Earth's surface. So the main verb we use here when we talk about sediments and sedimentary rocks is depositing these sediments, or deposition. So that's the laying down of these materials at Earth's surface. Sedimentary rocks are really important because they give us so much more information about what's going on the planet in terms of life at that time, because these are more or less exclusively the rock type that give us fossils. But they also tell us a lot about the environment. So they tell us things like we might have had a sand dune in a location at one time, or there was a lake here. We might even be able to tell which way the wind was blowing or the streams were flowing based on analysis of the sedimentary rock record. And so there's a real treasure trove of data here that we can dive into. And so for that reason, the sedimentary rocks are oftentimes very scrutinized and studied because they tell us so much about what was going on Earth's surface. I mean, fundamentally, like a basalt or granite is just telling you had magma. Now, obviously, you can tease more information out of that, and we've discussed that in our igneous rock series. But the sedimentary rocks, you can make an argument that there's just so much more information that can be gleaned from this group of rocks. Sedimentary rocks are usually deposited in layers or beds. You won't see that a lot with the samples I have because they're fairly small. They're basketball size or smaller. But realize when you go out and look at outcrops or cliff faces in nature, you're going to typically see layers, or what we call beds, or collectively this is called bedding, with sedimentary rocks. Those layers might be very thin, might be only a millimeter, or they can be quite thick. They can be so thick that you might not even recognize that the rocks are layered because it's on such a massive scale of maybe hundreds or thousands of feet. And realize that the information you can get out of an outcrop outside is so much better than a small sample. So the struggle I have as a geologist is people bring me their rocks or show me pictures of their rocks, and they ask me to like tell the whole story, and I'm like, gee, if I would have been there with you when you collected this rock, I might have been able to tell you some more things. So realize you can always get much more information when you're kind of out there in the field. And ultimately, our goal with any sedimentary rock, other than identifying it and giving it a name and classifying it, which is valuable, excuse me, the real goal is to determine the depositional environment. That's the story. That's actually what sort of environment or process or setting is responsible for that sedimentary rock. So that's really what we're looking for with these sedimentary rocks. And I'm going to come back to that in a little bit here, this idea of depositional environments, because that's really what hopefully you should be going for. Not just identifying that your rock is a sandstone, but hopefully being able to do the detective work, put together the clues and the information, and be able to determine what the setting was at the time that sandstone was deposited. Was it a beach? Was it the flood or the channel of a river? Was it a sand dune? Exactly what caused that specific rock to be deposited in it. Okay, so moving on. We're going to look broadly at two types of sedimentary rocks. So they get broken up into two groups. Okay, just like our igneous rocks were extrusive and intrusive. We divide our sedimentary rocks either into clastic, which is also sometimes called detrital. So the clastic rocks are rocks made out of weathered rock fragments. So chunks of rock that are, broken down from existing rocks and then get deposited and then get cemented or lithified together to form some type of sedimentary rock. These groups of rocks, we're going to mainly focus on the size of the grains and a few other features. That's going to be our main criteria for classifying the clastic rocks, is focusing on the grain size. Is it large or small? And we'll go over that here in a second as we continue on. The other big group of sedimentary rocks is what we call the biochemical sedimentary rocks. Now, classification systems vary. I sometimes joke that classification systems are kind of like belly buttons. Everyone's got their own. But this is what I use. So we're going with the Willsey way here. And sometimes these are divided out into chemical and biological sedimentary rocks, but I like to lump these together as the biochemical sedimentary rocks. Plus it makes it tidy that there's two types, but you really could divide these into three if you wanted to. And these rocks are made out of either organic material, so shells, fossils, plant material, things that were once living, or they could be made out of chemically precipitated minerals like salts or different evaporite processes. This group of rocks here, the biochemical rocks, we're going to mainly focus on composition. We're going to focus on, well, what kind of minerals are these rocks made out of? So one classification focusing on grain size dominantly, and another one looking at composition. And so we'll see if we can make heads or tails of these. Obviously, the classification system makes things nice and tidy, and then we start looking at the rocks and things get a little bit screwy and a little bit messy. So when we start with grain size, so grain size is a important criteria to look at when you're looking at sedimentary rocks. And if you want to get into deep in the weeds here, there's actually if you take a sedimentology class or read a sedimentology book, excuse me, you can look at a whole range of names that you're probably familiar with that define and describe sediment sizes. And some of these we just use in everyday life, right? So clay, you got silt, sands, granules, pebbles, cobbles, boulders. But we're gonna go with something a little bit more generic. And these do have specific classifications in terms of their sizes in millimeters. But you're gonna be hard pressed to pick up a rock and be able to tell just by your own observations and your naked eye that you have a rock that's made out of, medium-sized silt, or maybe something, it might be difficult even to tell these a little bit apart. And so to just generalize things and just get us on our way and not get too bogged down in the weeds, we're going to use the Willsey way, which is what I like to teach with my one-on-one classes. Obviously, if you work your way up into higher upper division geology classes, you can start to take this apart and get into the weeds with the details and sort of defining each one of these. So we're going to use gravel, sand, and mud as our 3 grain sizes for sedimentary rocks. Well, how are you going to tell these apart? I think you already have an intuitive feel that gravel is bigger than sand and sand is bigger than mud. But let's go a little further. Gravel technically is going to be everything above, we can kind of get both of these in here a little bit, everything above 2 millimeters in size. Well, are you going to be able to know how big 2 millimeters is? Maybe you've got a little ruler in your pocket. But in general, the diameter of a toothpick is pretty close to about 2 millimeters. So if the grains are a little bit smaller than a BB, or again, the diameter of a toothpick, or larger, we're gonna call all that stuff gravel, regardless of if it's a car-sized boulder or a golf ball size particle or a little BB, okay? We're just gonna lump that all together, which is even done on some of the classification systems here, like the Wentworth scale, as gravel, okay? Everything in that size range we're gonna call gravel. If it's smaller than that, if it's technically from 2 millimeters down to about a 1/16 of a millimeter, we're gonna call that sand. And you should have a good feel for sand because you probably have done some projects where you've dealt with sandpaper. And so the nice thing about sand is it has a gritty feel to it. So there'll be a tactile feel in your hand when you have a rock that's made dominantly out of sand-sized particles. So we can divide that sediment size that way. You might be able to tell that the sand is, because sand is still large enough to be seen with the naked eye, you might be able to tell if it's coarse sand versus medium versus fine sand, but you might not know exactly, well, is this very fine sand or is this fine sand? Well, again, that's kind of a little bit deeper in the weeds, and you can use something like this Wentworth scale, to determine that if you so choose. But back to the Willsey way, our last sediment classification for grain size is going to be mud. So anything smaller than sand, and as you feel it with your fingers, it's going to feel smooth to the touch, not gritty like sand. We're going to call that mud. And of course, mud is actually a term that we use to describe both silt and clay. So this is somewhat of a generic term here for both silt and clay-sized particles, which are hard to tell apart to the naked eye, even with a tactile feel. You're going to usually need some other tools to tell these apart. Old-time geologists would sometimes put these in their mouth, and the silt will feel a little gritty, the clay will feel smooth. I am not advocating that you stick sediment in your mouth. I don't want to be responsible for that. So you might even find on the internet, this one's not, this is too small, I should blow this up, but you can actually find little scales like this that you could take with you, maybe laminate, put in your pocket. You'd of course want to make sure that you get these blown up to the right size so that the very coarse sand, 1 to 2 millimeters, that those dots are actually 1 to 2 millimeters in diameter. But this might be a nice little handy tool you can use to kind of help you on your way a little bit, okay? Okay, so the last thing we're gonna cover on this page, and then I'll actually show you a couple rocks here. So if we stay with the idea of grain size, let's think about how those grain sizes are distributed. If those grain sizes are pretty much all the same size, we call that well sorted. So this distribution of grain sizes is a term we call sorting, okay? So if everything's pretty much the same size, all the particles or all the sediments in the rock, we call that a well sorted rock, okay? Versus if we have very different sizes, maybe huge chunks of sediment, gravel-sized particles that are as big as your fist, all the way down to sand and even mud-sized particles, that would be a poorly sorted rock. Realize that this is a spectrum, okay? So this is actually a spectrum that kind of goes from, well sorted on one end of the spectrum over here to poorly sorted. Okay, so you might end up with something in the middle that's kind of moderately sorted, that sort of thing. And let me just show you a couple rocks here to kind of illustrate this a bit. So here's an example of a poorly sorted rock. We can see it's got big gravel-sized particles in here, glued together, but we can also see there's some very small particles in here as well. So sand-sized particles, and probably even down to mud-sized particles if we look as well. But a fairly generous range of sizes within the rock here. So this would be an example of a poorly sorted rock, as opposed to this lovely sandstone from southern Utah. if we zoom in here closely, about as close as we can, we see that all the little grains of sand in here are pretty much the same size. There's no real change in the sizes of these particles. They're pretty much all the same. So this would be an example of a well-sorted sedimentary rock. So poorly sorted, well-sorted, those might be good adjectives or phrases that you can add to your lexicon as you're describing and looking at sedimentary rocks. Okay, back to the paper. Lots of notes today. I'll make sure I put these notes up in the link, so if you want to copy these or print these out on your own, you're welcome to have at them. So the next thing we're going to look at with respect to grain sizes is grain shape. And the shape of a grain or a sedimentary particle will be dictated by how much transport it's endured or how far it's moved through a system, or how much time it's been transported perhaps, and also how hard the original particle is. So if we have a sediment particle that's soft, maybe something like halite, like salt, right? We talked about that with minerals. That's not going to last very long. So every time those particles collide, that's going to make it break apart into smaller pieces. And so it's probably not going to get transported as far as something maybe like quartz. So you can also find nice little examples like these on the internet where we use sort of another spectrum of phrases or adjectives to describe the shape of the grain, going from very angular with lots of little points and sharp protrusions along the edge of the particle. And then as we work our way towards the other end of the spectrum, we can see that those edges are becoming a little bit more rounded until we end up with something that's well-rounded itself. Notice here we have two different overall shapes. You might have a particle that's spherical, meaning it's sort of like a sphere or a ball or rounded, or you might have something that's more oblong or oval shape. And so you can see some variations there. Let's see, I do have a couple pieces over here just to kind of show you some different sample sizes, but I wanted to show you that these are both considered rounded, even though their shapes are different, right? This one over here in my right hand is kind of shaped like a disc, okay? But it's very rounded, okay? This one over here is more spherical, like a ball, and it's also quite well-rounded. So these are both well-rounded pieces of sediment, even though their shapes are different. So really what we're looking for here is the lack of any sharp little corners or edges. And basically how these have formed, if you're not aware, is that these are sediments. Now these are big pieces of gravel, but these could also be small pieces of sand or even mud. But as these get transported, maybe in a river, maybe sitting on a beach in the ocean, maybe by the wind, if these are sand-sized grains, as these particles collide, as they're being transported, collisions with each particle is what actually breaks off the sharp little corners and ultimately produces these more rounded rocks. Typically, when you see very well-rounded pieces like this, they're gonna tend to be very hard and resistant, usually quartz-rich. But the point is that they have a mineralogy and a composition that is much more hard and resistant, okay? So just a couple of different examples there. This one's a little less rounded, has more angularity to the shape versus something like this, right? But this would still be a probably sub-rounded to rounded particle. This is what I would probably call a well-rounded. And you can use those little charts to compare. These are all well-rounded, actually. They're just some different shapes I just wanted to show you here. And these are mostly, we'll get to these rocks later. These three here are quartzites. These two are volcanic rocks. This looks like an andesite or a dacite. This one's maybe a granite. And this one also maybe is definitely igneous, maybe a granite as well. So quartz-rich rocks there. Okay, and I did mean to look quickly at grain size. So just kind of put out some little trays here to kind of show you I think everyone knows what gravel looks like, but there's some nice gravel particles. If you look at the shapes of these grains, we can see that they range a little bit, and if we used our handy dandy little chart like this, we could kind of compare them, but it looks like we have some subangular grains, some in here that are more rounded, like this one here is more of a rounded particle here. Anyway, but I just wanted to show you the grain size from gravel to sand. We can zoom in a little bit more here. And this is where, when you get to the sand-sized particles, a hand lens will be really helpful to you to actually look at these particles up close. I don't know if the camera doesn't like that. But anyway, you can see the sand-sized particles. I can't really tell the shape of these particles without using a hand lens or even a simple microscope to tell me what the shape of these grains are. If you have access to a simple like stereo microscope, which aren't very expensive, they're maybe a couple $100, boy, you can just go crazy looking at sand because you can see composition, quartz, mica crystals, rock fragments, feldspars. You can see, of course, the shape of the grains, and that can really add to your kind of sedimentary rock fun. And then over in this tray, what I put, this is clay. And so that's actually a clay stone, or I guess we could call a mudstone. We'll get to those later. So I can kind of break these apart and just kind of pulverize it with my thumb and forefinger. But then what I end up with here on my fingers is this very fine, powdery, it's smooth to the touch. This is clay. This is what clay looks like here, as opposed to the sands, which has more of a gritty feel to it. So there you go, messy fingers. Okay, a couple more things and then we'll wrap this up. One last thing on grain shape, this is important. And I think we saw this with one of the samples I showed you as well. Realize that your rock can have more than one shape in it, right? So you may have a rock that has the whole spectrum, right? From well-rounded to very angular grains. There's nothing wrong with that. It's telling you a certain story. It's something you need to figure out in terms of the history of the rock. But that's totally permissible. So it's not like specific rocks are just going to have a specific shape. If we come back over here to this conglomerate, we can see some fairly rounded shapes in here, but I'm sure if we look and hunt, yeah, like this one here, let me zoom in on this little particle. This one here, gosh, it has like a 90-degree angle to it over here. There's kind of a little protrusion sticking out over here. So this is at least probably subangular, this specific particle here, and you might even be able to find some in here that are more in the angular realm as well. The point is that we have a variation in terms of shapes of the grain embedded in this rock, and that's fine. That you just observe what you observe. Don't try to pigeonhole the rock into fitting one or the other. And also make sure that when we talk about grain shape, we're talking about the grains in the rock. We're not talking about the overall shape of the sample, right? That's not what we're talking about. We're talking about the particles inside it there. I didn't show this one, but I meant to just show that sedimentary rocks have fossils in them. So there's a nice little clam fossil. It's a Eocene rock from, I think it's Eocene. No, it must be younger. It must be Miocene. That's from the coast of Oregon. Okay, last couple things here. We talked about depositional environments. This is what you're trying to do, right? This is your goal in looking at your rock, is to identify it, come up with some good observations, but then ultimately figure out a setting where this rock formed. If we have something like a sandstone, well, where do you see sand forming? We see sand at the beaches. We see sand sometimes along river beds or the banks of rivers. We sometimes see sand in sand dunes. And you might think of other environments. So it's a setting. It's not a specific location. It's not like, Beverly Beach, Oregon, or, excuse me, Great Sand Dunes Monument, Colorado, because we're looking at rocks that are ancient. So we're not concerned about the specific location geographically. We're concerned with the location or the setting where that rock might have formed. So here, just an examples of some possible, and the list could go much, much longer than this. When we think about depositional environments, think about energy level. You have to have an environment. You should make sure that your depositional environment matches your rock. So if I have a sandstone and I'm telling you that the sandstone formed in a swamp, well, that doesn't jive, because in a swamp we have no transport of sediment. It's very slow, stagnant water. There's a lot of organic material that will tend to build up, but there's no way to transport sand-sized particles in a stagnant swamp. And so we want to make sure that the depositional environment matches or is a likely match for the type of rock we have. So think about energy level. If you've got something like this with large particles, gravel-sized particles, that takes a lot of energy, right? It takes a lot of energy to move something as big as a golf ball in nature. So this would maybe be a river or a beach or maybe a glacier or something like that, right? Some sort of process that can move particles of this size. Versus if I have something that's much more fine-grained, like the sandstone, I've got to be making sure that I'm thinking about the energy it takes to move sand. Well, wind can move sand and water can move sand, but I want to make sure it's consistent with those observations. So, and then ultimately what we try to do is use everything we have, right? So we look at the rock, we look at the fossils, if it has any, we look at the size of the grains, the shape of the grains, what the grains are made out of, possible sedimentary structures, which I'll talk about here in a bit, to tell us what the depositional environment might be. So that's hopefully a good summary of just introducing you to the world of sedimentary rocks. Excuse me. The rocks that I am sort of planning on, at least at this point, are as follows. I don't know if each one of these will get its own video. I may lump some of these together, maybe not. So these top three here are clastic sedimentary rocks, conglomerate, breccia, diamictite, sandstone, mudstone, and shale. And then these bottom four or so here are biochemical. So we'll cover those, or I guess that's only three. This is actually not a rock type here. So limestone, there's all sorts of varieties of limestone and dolostone, chert, different types of coal we can look at. And then I may do a video also on sedimentary structures. So these include things like ripple marks, mud cracks. I don't know why I'm writing these down. Kind of fun to do. Oh, the pen's dying though. Mud cracks, cross bedding, graded bedding. This one, we'll have to see how it goes and what kind of samples I can put together. So, but that's the idea, team. Hopefully this is helpful. Hopefully you've learned a couple things here about the sedimentary rocks and just kind of an introduction to sedimentary rocks. I'll put all these notes here up as a link under the description. If you like what you see, please make sure you like, subscribe, share, do all those good things. And then also I have a donate button as well at the top of the banner on the YouTube page, and a link in the description as well to a PayPal account if you want to support the channel and the content that you're enjoying here. Appreciate it. I guess I could turn around and give you a farewell, sign off. Thank you for joining me. Rock Identification with Willsey, Introduction to Sedimentary Rocks, and we'll be with you next time with, I guess, our first sedimentary rock video on conglomerate, breccia, and diamictite. Thank you.